Hello and welcome to the 2021 Photonics Spectra Conference, hosted by Photonics Media. In this track, we're covering the latest in lasers applications, trends, and developments in instrumentation with experts in the fields. I'm Sarah Weiler, and I'm the Photonics Media Webinar Coordinator. You're joining us now with Dr. Greg Quarles, CEO of Applied Energetics. In this session, he will be speaking on directed energy lasers, a historic and future perspective. Welcome, Greg.
Thank you. Good afternoon, everyone. I'd like to thank the team at Photonics Spectra for the invitation to attend and present at the virtual conference. My name is Greg Quarles. I'm the CEO at Applied Energetics in Tucson, Arizona. I've been honored to work in the directed energy field for over 2 decades. And today I'd like to share the history of the directed energy space, as well as my perspective on the future and the directions that directed energy platforms are taking with innovations in this field. Applied Energetics is a company that's been around for 20 years, working almost exclusively in the directed energy space, and I'm honored to be a partner with them. What I'd like to share in the presentation today is the overview of the threat solutions using directed energy that the platforms enable us to focus on. These are high technology devices that I'll be talking about today, and they're typically lasers that are going to be working outside of the lab. They're not going to be on a isolation table, and they're not going to be in a clean room. So there are a lot of environmental issues that go with these, as well as size, weight, and power constraints that typically come in. And I'll try to walk you through the developmental history of a lot of this up to where we are today and what new breakthroughs need to take place. So I throw this slide in to ask the first burning question of, is Archimedes really the godfather of directed energy? It was speculated that in the Battle of Syracuse off of Italy, that he used mirrors to focus the sunlight onto Roman warships and set them on fire over 2,000 years ago. Today, scientists and engineers are trying to utilize the breadth of the electromagnetic spectrum to explore solutions to various threats that are out there, and not so much these warships. The spectrum shown here spans everything from the radio frequency through visible near infrared, ultraviolet, out to gamma rays, and microwaves. And much of this is utilized on a variety of directed energy platforms. These platforms will sometimes be standalone, and other times they will be used together to try to use multiple parts of the spectrum to defeat threats. So why directed energy? Today I'm going to focus, almost exclusively on the optical portion of the spectrum. As shown in the image here, you have microwaves, you have optical sources, you have lasers that are used on a variety of different types of threats. But the greatest portion of the funding currently is going into the optical sources. And why would that be? Well, as shown here, it provides the attack of the threat at the speed of light. It has very precise targeting, and you can engage multiple targets at once. And in the environment that we're in today, that's where we see a lot of it moving towards, is not just one threat flying at you, but potentially hundreds of them flying at you very fast. So engaging these at the speed of light is a more rapid way to do it than using ammunition. And your ammunition, your photons, are essentially unlimited with the size of the magazine that you have. This particular slide shows the directed energy types of threats that are out there and where they span across the various portions of the spectrum. In the middle, you've got electromagnetic pulses, can be used to damage certain threats. And around the perimeter, you have particle beams and millimeter waves. Most of those are not in use in the field currently, but the two top quadrants are, and that being the high energy lasers and high powered microwave and radio frequency types of technologies. This is where a majority of the funding is going currently. This is where a majority of the research is taking place at the university labs, as well as in federal research labs, government laboratories, small and medium-sized businesses, and then the typical defense primes that you would see out there. So we'll be focusing on the top two portions as we go through the rest of the presentation today. The three types of beams, as I will call them, that are defined as directed energy systems. Top left is what a high power microwave device would look like out in the field. Large dish mounted on a large truck, pointing the beam at something flying at it. In the middle is laser guided energy, which is the most recent of the designated directed energy systems, was developed at Applied Energetics and uses electric discharge essentially, and over the top of that using a ultra short pulse laser to guide the electric discharge towards a threat. So to the block of an engine, to an IED, to some sort of an explosive to defeat that threat. And then on the bottom right, you have a laser system, CW laser that's mounted shipboard to try to defeat threats that are flying directly at the ship. All of these are important. All of them are being funded in one way or have been funded in the past. And they're important to the optics and photonics community because many of these technologies involve lasers and optics and windows and other types of technologies that our community supports. I think it's always worthwhile to look at the timeline of the evolution of these types of technologies and understand where we've been, what's taken place, and why. And as most of you know, the laser was invented back in 1960, so over 60 years ago. And we're just now getting solutions out into the field that encompass lasers and other optical sources. Reading from left to right on the slide, the CO2 lasers were the first type of lasers that were engaged in directed energy types of applications because back in the 1970s, the highest output power that you could get was with the CO2 laser. But that became cumbersome to move into the battle space. It became cumbersome to maintain. So there was a move towards using chemical-based lasers, either on aircraft or on the ground, to try to generate these high powers and defeat threats. In the late 2000s, most of those were determined to be not feasible, primarily due to size, due to toxicity, and due to a lack of mobility. And starting in the early 2000s, late 1990s, the switch was made to starting to look at the advancement in solid state lasers. So the capacity laser at Lawrence Livermore and other lasers being developed up through the joint high power solid state laser that you'll see here shortly. And over these last 20 years, we've seen an evolution of the technology to where most of the directed energy platforms now are all substantially either distributed gain media or solid state lasers of one sort or another. This particular roadmap shows the various types of lasers that have been funded by the Department of Defense, the types of output powers that were achieved, and where they fit within the tactical and the strategic roadmap. You can see on the left axis, laser scaling in power from a kilowatt to tens to hundreds to thousands of kilowatts or megawatts. And I think the trend that you see and focus on here currently is the red line, which are the solid state lasers. And from 1960 to the late 1990s, those were all hovering in that 1 kilowatt regime. And then the solid state lasers started to take off in terms of being able to develop more and more output power to be manageable. And the arrow on there shows that they're continuing to grow from the tactical space at 100 kilowatts up to some of the lasers that you'll see shortly being developed and sold to the DoD in the 200 and 300 kilowatt regime. So currently these are the lasers that are the ones that are the go-to type of technologies and platforms for the Department of Defense. And why has that happened? Well, most of the technology that you see here have had limits and have peaked out either because of size or thermal capacity to be able to get rid of the heat or the ability to have enough pump power to achieve these megawatts of output power. In the year 2000, the Directed Energy Joint Technology Office was established in Albuquerque to start developing and focusing on the evolution of lasers for directed energy platforms. And the first large program that they concentrated on was the JHIPSL program. And this particular program, run out of the JTO office, included research from some of the best universities in the country, from small businesses, from federal research labs, and then all the way up to the primes. And over this 9-year span, it went from multiple programs looking at various aspects of directed energy to a final program being funded with Northrop Grumman to develop what you see on the top left here, which is the joint high power solid state laser 1 kilowatt coherent beam combined program that was then shrunk in size and placed on a Navy defense ship later in 2009 and into the 2010 era with 100 kilowatts out on the water. Others that contributed through the competition and through the evolution of the technology included General Atomics, Textron, Raytheon, and Lawrence Livermore National Labs. So it was really a joint effort with one winner that was down selected to provide this technology to the government. The real critical thrust that took place here was going from this large size that you see on the leftmost picture to a size that was shrunk down through size and weight and thermal restriction reductions and power increasing coming out of the multi-head system that was involved. This particular slide shows a number of other lasers that are electrically pumped, that is pumped with laser diodes and other optical sources to scale them up to 50, 100, 150, 300 kilowatt classes. The top left is a coherently combined fiber system. Bottom left is a distributed gain system from General Atomics using multiple tiles of laser gain material and diode pumping. Upper right is spectrally combined fibers on the Relay program, in which Lockheed Martin is demonstrating 100 kilowatt class laser systems. And the bottom right is the 30 kilowatt class laser from the diode pumped alkali laser system that was initially developed by the team at Lawrence Livermore with Bill Krupke and is now advancing out of the lab to advanced stages to where they're projecting this to be over 300 kilowatts in the next decade. So all of these lasers are utilizing optical pumping of the laser gain material and constriction of size and getting size, weight, and power down. It's primarily been done through, as you can see here, coherently combined and spectrally combined fibers, things along those lines. It's multiple small lasers built into these housings, and then those small lasers are combined along optical paths so that there's a single high power beam coming out. The generation of this to demonstrate 100 to 300 kilowatt class systems has only been achieved through the combination of these multiple lasers internally. From 2011 to 2017, the next phase past Jay Hipsel is the Robust Electric Laser Initiative, the Relay program. And again, it shows a lot of the same technologies that I just mentioned previously, the combined beam, the coherent beam combination, distributed gain lasers, planar waveguides, and spectral beam combinations, getting the swap down, the size, weight, and power to where it can be, generating higher laser efficiencies from the electrical to optical coefficients being improved, and getting strong power in the bucket measurements from the beam on the target have all led to these technologies from these primes being released on things like ships and Army vehicles and aircraft and UAVs. So it's something that over the last 20 years has really been a revolutionizing technology for the directed energy space. And I think we're seeing that a lot of this is taking place because there are emerging threats that are escalating currently, and they have to be defeated in one way or another, and that's only through higher powers coming out of these laser systems. But this particular graphic, I think, really shows that there has been a large industrial contribution to the evolution of directed energy platforms. And what you can see here are the evolution of high power diodes becoming more cost effective through fiber coupling of the light coming out of the diodes, and taking those pump sources and combining them to either pump other gain materials or spectrally combining the light out of the fiber to come out of the laser and go on to target. And the two key things that you can tell with most of these are that there's been size reductions, there's been power consumption reductions, and there's been weight reductions. And all of those tend to be able to drive these lasers from strictly being used on very large, heavy platforms or trailers out in the field to actually being able to be used on things maybe as small as an unmanned vehicle in space. So this is a 20-year evolution that has really been driven by the supply chain, and that's what it's going to take for these processes to continue to evolve and gain higher powers. So what does it take to manufacture a laser system for directed energy? I think that this chart really shows graphically that it's not just a laser and an optic out front. There are a lot of combinations of technologies that have to go in, and many of them that are still in a maturing phase. All of the elements that you see here on the left for the laser source include thermal management of your pump sources and your gain material, combining those beams, beam conditioning optics to get a highly diffraction limited beam downstream, power conditioning so that the power coming to the laser is constant and not changing. Then that has to go to the beam control in the center, which allows you to take the beam and point it at a target. That takes windows, that takes mirrors. It takes a wavefront sensor to look at what's happening with the atmosphere out in front of the laser so that you can correct for it back at the laser beam itself. An illuminator, fire control, something to look at the target and say, is this a friendly or is this a threat? Can you identify the threat? How's it flying? Put that light on the target as it goes. Get the light through the atmosphere. There's turbulence, there's thermal blooming that takes place with these CW beams. And then finally, you have to damage or destroy the thread out in front of you. So your beam has to be a reasonably clean beam that can be put on there and have the damage effects that you want to have. So all of these have to talk to each other eventually. When you put it on a ship or put it on a platform, you have to look, you have to scan the sky, you have to point, you have to track the target, and you have to put the photons on the target. And then all of that has to keep running in an environment that's 120 degrees or minus 20 degrees with sand or snow or moisture. So it is a complicated non-laboratory tool that a lot of people are investing a lot of time and resources into. And these are areas that industry and the supply chain can really contribute to. If you look at the growth of the strategic roadmap for high energy lasers, currently we're in this tactical phase of 100 kilowatt lasers being delivered to the DoD on a routine basis. That's going to grow over the next 5 to 10 years to 200 to 500 kilowatt class lasers taking on tactical missions to be able to encounter things like drones and cruise missiles and other close combat type of ammunition. And then past 2030, they have a goal of reaching megawatt class lasers, 1,000 kilowatt class lasers to take on ballistic missiles as well as hypersonic missiles that we read about daily. So all of these are going to take continued growth in the area, continued output power, and each of these is going to be another stage in industrial quality control and industrial supply chain development. And how has all this been realized? Well, it obviously takes funding, and the US Congress has been very diligent in their funding over the last decades. They've looked at this as a way to provide a threat defeat mechanism for the Department of Defense and other agencies in the government. And so over the last several years, in 2017, the federal budget for directed energy platforms was a little over 500 million. The 2021 budget we expect to be over 1.8 billion to investigate the research, development, deployment, and use of these technologies in the field. And it's going to continue to grow as the threats continue to grow. But this double-digit year-over-year investment by the government has really paid dividends in terms of jobs, employment, and research and development taking place within the federal government and others. As I mentioned previously, one of the new technologies that has been emerging is the use of ultra short pulses that is pulses that are less than a picosecond to try to defeat some of these threats in conjunction with the CW systems. And why is this important? Well, if you think about swarms of high-flying, fast-flying, small mobile targets, you can't just sit there and try to lock on with one beam and hold the beam there until it burns the target out of the sky. You need to look for technologies that can hit the target in a billionth of a second and put a billion times more peak intensity on that target than the CW beams do. CW beams have their place. Now the ultra short pulse is starting to emerge in these areas to do single shot threat defeat, to do reduced dwell times on the targets, and to emerge as the complementary technology to the CW technology that's already out there. The CW beams also allow for different target effects to take place than the CW beams do. The CW beams are there for thermal effects, to burn something and destroy it. When you use ultra short pulse, what ends up happening is there's a nonlinear response in the atmosphere. If you get a high enough energy pulse, that pulse now starts having nonlinear effects going through the atmosphere. And instead of diverging like a normal beam would do, you end up having something called self-focusing. Essentially, the atmosphere turns into a lens, and you have something called whole beam collapse, where the beam may be 10 millimeters in diameter when it starts going through the atmosphere, and it can compress down to hundreds of microns in diameter through this nonlinear effect that ends up causing filamentation, and it can essentially put very, very high intensities up to a terawatt of peak power onto the surface of your target, which can then have differing effects when it hits that target. And the laser material interaction with the CW beam, it's typically going to diverge as it goes. The self-focusing beam in the top left quadrant of this shows the damage mechanism where the beam focuses down very tightly. You can do thermal damage, you can do mechanical damage. You can also hit the cameras and the sensors that are on there and essentially damage the surface and the response of that sensor. Or you can hit the surface of the target, the threat, and after the photons hit that surface, that interaction that takes place generates radio frequencies, and those radio frequencies can then jam the electronic circuitry in the threat. So you have multiple effects that can come in through ultra short pulse that's now starting to evolve from the laser lab into the test arena. And what that also allows you to have is the ability to go onto much smaller platforms and be able to have those platforms be mobile out trying to work and defeat those threats. On the left side, you see the type of platform that an ultra short pulse laser can go onto and consume maybe 55 to 100 pounds and only a kilowatt of power. On the right hand side is what the CW 50 kilowatt lasers typically go onto, and they may be, 500 pounds and consume several hundred kilowatts of power to operate. So you have different operational regimes here and different effects that you have on your threats. We also need to look at what are the other areas that these ultra short pulses can evolve into. And there are areas in the commercial sector which include additive manufacturing, subtractive manufacturing, medical imaging, and manufacturing of biomedical types of devices. So there is a second dual use application for the technologies that are being worked on currently in the lab, just like there are with the high power CW systems that are used in cutting and welding technologies currently on the machine shop floor. And then finally, looking at the industrial based challenges, what should we be looking at? What should we be trying to understand as an industry in the optics and photonics realm to try to determine where the investment goes and what needs to be done. And as always, when you generate lasers with more power, you have to have higher damage threshold optics. For a lot of these laser systems that we showed the integrated image of, you need adaptive optics and advanced jitter controls so that the beam can stay on target and be focused where it needs to be focused in the atmosphere. You have to develop power and thermal management systems. You're not going to have a chiller or a cooler strapped to your mobile command when you're out in the field. You're going to have something to pull the heat away from the laser. You're going to have to look at high volume manufacturing, the diodes and the laser gain media. I think that's coming along nicely. You have to have things like understanding at the fundamental level, how do the laser beams propagate in the atmosphere and what happens when the laser hits certain types of materials, both as a function of wavelength and a function of pulse width. And then finally, standardization, quality control, ruggedization, and the ability to use these lasers that are evolving in public spaces. They've got to be eye safe, they've got to be non-lethal. You can't be hurting the public around in an area where you're going to be trying to use these lasers. So there are a lot of opportunities for supply chain and industrial base to contribute here and to generate revenue. And with that, I wrap up. I acknowledge Patrick Williams and Steve McCann at Applied Energetics for assisting here, the Directed Energy Professional Society for all they do to support this group of researchers and engineers that are out there to have a forum to be able to talk about and discuss these technologies and advance the competitive technology base. And with that, I'll leave it and answer any questions you may have. Thank you again for your attention today, and thank you for your interest in directed energy history and evolution.
Great, thank you very much, Greg. Before we close, I do have a couple of questions. My first one, how do ultra short pulse lasers complement the current continuous wave lasers?
I think the biggest complement is in a situation where you have a lot of threats flying at you at once. A CW laser may take several seconds to dwell on a target to be able to burn it or push it, to take it out of the sky. Whereas if an ultra short pulse laser can intercept that target in a billionth of a second and disrupt it through radio frequency generation or burning it, now you can move from target to target in less than a second and try to engage and destroy the threat.
All right, I got one more question. What do you see as the biggest challenge for the industrial supply chain for delivering these technologies?
I think right now the largest challenge is going to be moving from the 1 micron region, which is where many of the CW systems are, out to other wavelengths that have transmission through the atmosphere, because it's going to take coatings that are made of different materials, optics that are transmissive at different wavelengths, adaptive optics that are going to respond at wavelengths other than just 1 micron. So I think that's the whole supply chain has to be broadened to incur other wavelengths as well as a variety of different pulse widths and not just continuous wave.
All right, well, thank you very much, Greg, and thank you everybody for participating in Directed Energy Lasers, a Historic and Future Perspective. This is part of the 2021 Photonics Spectra Conference Lasers track, hosted by Photonics Media. We're your source for global photonics news and education. You can explore more talks on lasers and customize your personal event schedule on the Photonics Spectra Conference website. If you have any questions about the conference or how to use the site, please see our FAQs. Thanks for attending. Thank you very much again, Dr. Greg Quarles.
Thank you.